Today I will be exploring the Maillard reaction. The Maillard reaction is a chemical reaction between amino acids and reducing sugars that gives brown food its distinctive flavor. It was first discovered by French chemist Louis-Camille Maillard in 1912 while attempting to reproduce biological protein synthesis. Seared steaks, caramelized onions, cookies, breads, and many other foods undergo this reaction. The reaction typically proceeds rapidly from around 140 to 165 degrees Celsius. At higher temperatures, caramelization, which is the browning of sugars, and pyrolysis, the final breakdown leading to burning, becomes more pronounced. The reactive carbonyl group of the sugar reacts with the nucleophilic amino group of the amino acid and forms a complex mixture of molecules responsible for the range of aromas and flavors observed. This process is accelerated in a basing environment as the amino groups are deprotonated and hence have an increased nucleophilicity. In the cooking process, Maillard reactions can produce hundreds of different flavor compounds depending on the chemical constituents in the food, the temperature, the cooking time, and the presence of air. These compounds, in turn, often break down to form yet more new flavor compounds. Today I'm going to be using onions to explore how the Maillard reaction is involved in cooking food. So here are my onions, and I'm just going to be cooking them in this pan on the stove in a little bit of oil for the first part of it. Then, once they've cooked for a little bit, I'm going to add baking soda, which is sodium bicarbonate, to create a basic environment, and then you'll be able to observe the Maillard reaction. Okay, so I'm going to be adding my onions now. And I'm just going to cook them a little bit in the oil. So as the onions are cooking, you can kind of hear like that popping sound you associate with frying food, and that's actually the water leaving the onions. And the water is also the reason why the onions have not started to change color yet, because the water is preventing the onions from getting to 100 degrees Celsius, and it can't undergo the Maillard reaction until it gets above 100 degrees Celsius. So now what I'm going to do is I'm going to separate my onions into two halves in order to do a little controlled experiment. So here we have my two halves of my onions. And what I'm going to do is to one half I'm going to add my baking soda. So you can see the white powder there with the baking soda, and then this half I'm not going to add the baking soda to, and you'll be able to see the change that the basing environment is causing in the onions to allow the Maillard reaction to happen more rapidly than in the onions without the baking powder, or baking soda. hard to see on the camera, but if you bring it closely, you can see the onions with the baking soda over here have started to change color a little bit, and there's a lot more liquid coming out of them than the onions without the baking soda. A little bit more baking soda, just to make sure it's really basic. Okay, so here I have my finished onions, and we can see the comparison of the Maillard reactions happening. So in the one with the sodium bicarbonate and the one without the sodium bicarbonate, we can see this one, it changed color. You can see like the golden, it's kind of hard to see in the camera, but these are more yellow. You can definitely see it here, like the golden brown. And then these ones still are pretty white. Also, the ones with the sodium bicarbonate are a lot more broken down, as you can see. Like these ones still pretty much have their structure, they're pretty firm, but these ones have a lot more mushy, and you can see a lot more liquid has come out of them. So the explanation for that, like I said earlier, is the increased pH from the sodium bicarbonate or the baking soda. Sodium lowers the concentration of the protonated amine group, and the deprotonated amines have a greater nucleophilicity, and they are better able to attack the carbonyl centers of the sugar molecules. So the Maillard reaction occurs a lot faster in the basic environment than in the non-basic environment, as you can see. Okay, so as previously stated, the Maillard reaction begins with two reagents under heat, a sugar and an amino acid. In this mechanism, I'm going to be using dextrose for the sugar and then just a generic amino acid. As you can see, I'm using the deprotonated form of the amino acid in my mechanism. So this mechanism presents the reaction going on in the onions that were covered in sodium bicarbonate. The sodium bicarbonate increased the pH of the onions, causing the amino acids to take their basic form and for the nitrogens in the amino group to no longer be protonated. This freed up a lone pair in the amino acids, increasing the electron density around the nitrogen atoms, leading to a stronger nucleophilic amino group. The stronger nucleophilic amino group can now better attack the carbonyl group in the sugar. The onions which were not covered in sodium bicarbonate were not exposed to a basic environment, so they maintained their protonated form. The protonated amino group in the amino acids in these onions is not as strong a nucleophile as the deprotonated amino groups are, so it is not able to attack the carbonyl in the sugar as well. So the nucleophilic nitrogen in the amino group of the amino acid attacks the electrophilic center of the sugar atoms. This forms an aminium ion after a 1,2 addition to the aldehyde of the dextrose sugar molecule. So then the alpha carbon is deprotonated to create a double bond between carbon 1 and carbon 2. Now the lone pair on the alcohol of carbon 2 then pushes down to form a double bond, and the double bond between carbon 1 and 2 grabs a proton from water. Okay, the alcohol on carbon 6 then adds to carbon 2, cyclizing the molecule into an N-substituted glycosylamine. This compound is very unstable and can continue on to a vast number of rearrangements, forming a wide variety of compounds that contribute to the flavor and appearance of browned food.